We have properties of eigenvalues and eigenvectors. All right. So properties of eigenvalues, eigenvectors. I can, in fact, expand this. These are important properties. So just now, we checked this one. The sum of the eigenvalues of A is equal to the trace of A. The product of the eigenvalues of A is equal to its determinant. Now, eigenvalues of an orthogonal matrix is of unit modulus. Unit modulus meaning if this orthogonal matrix is real, you get a unit modulus. If eigenvalues are imaginary, then the modulus of those complex numbers is also 1 unit. So this is an important one. Eigenvalues of unitary matrix are of unit modulus. So orthogonal matrix and unitary matrix are similar. Orthogonal matrix is A inverse is equal to A, that is orthogonal matrix. A into A transpose is equal to I. For unitary matrix, if A into A conjugate transpose equal to I, it is unitary matrix. For both of these, the eigenvalues are of unit modulus. Next, A and A transpose have the same eigenvalues. Okay. Now, eigenvalues of not just Q Hermitian, I'll write here, I have to add. Now, eigenvalues of a symmetric matrix are real of skew symmetric matrix of a Q symmetric matrix are zero or purely imaginary. What is a skew symmetric matrix? How does a skew symmetric matrix look? How does a skew symmetric matrix look? The diagonal elements will be 0, and across the diagonal elements numerically will be the same, but the sign, they will be of opposite signs. This is a skew symmetric matrix. The trace of the skew symmetric matrix is 0. That means sum of all the eigenvalues must be 0, which is possible when the eigenvalues are 0 or purely imaginary and they appear in conjugate pairs. So it will be cancelled. So that is one. Next, what is the determinant of a skew symmetric matrix? Of course, this we will have to calculate. You cannot say it is 0. So based on that determinant, the product of the eigenvalues will be equal to the determinant. So here it is marked as Q Hermitian, but it is also applicable for skew symmetric. All right. Similarly, eigenvalues of a Hermitian matrix are real. So eigenvalues of Hermitian matrix are real, and skew Hermitian matrix are zero or purely imaginary. Okay. Next, if lambda is the eigenvalue of A, then lambda is the eigenvalue of A conjugate transpose. Just like A transpose is there, this is valid for that. A conjugate transpose also. A and A conjugate transpose will have the same eigenvalues. The eigenvalues of a triangular matrix are its diagonal elements. This is an important one. We can cross check it. It is not difficult. We'll cross check that. If lambda is the eigenvalue of A, k times lambda is the eigenvalue of Ka. So if a matrix is multiplied by K, then all the eigenvalues of A get multiplied by K. Those gives the eigenvalues of the new matrix. If lambda is the eigenvalue of A and determinant A is not equal to 0, then the eigenvalues of A inverse will be 1 by lambda. Okay, these are some important properties. Now, if lambda is eigenvalue of A and determinant of A is not equal to 0, then determinant of A by lambda is the eigenvalue of adjoint A. So adjoint A is nothing but A inverse is adjoint A by det A. And from the previous result, A inverse eigenvalues are 1 by lambda. All right. So from that we can deduce. This is not a difficult one. So A into adjoint A is determinant of A times I. This is what we know. So adjoint A is A inverse times this. So det A into A inverse times I. So now if lambda is the eigenvalue of A, then the eigenvalue of 1 by A inverse is 1 by lambda, and then K times A inverse will be K by lambda, and this K is nothing but determinant A. Determinant A is a scalar. So determinant A by lambda will be the eigenvalue of adjoint A. So these are simple objective questions can come from this. All right. And last, if lambda 1, lambda 2, so on up to lambda n are eigenvalues of A, then eigenvalues of A power k are lambda 1 power k, lambda 2 power k, so on lambda n power k. So we can show all of these. All right. So this is about eigenvalues properties. We'll see